Hello, this is Jake Abbott. In this video, I'm going to be talking about eigenvalues and eigenvectors. This should be a review of previous linear algebra classes, but it's an important concept that we're going to use extensively in this class, so I want to make sure it's fresh. So when we talk about eigenvalues and eigenvectors, what we're doing is we're solving a set of equations. We're saying we have some matrix A times some vector x, and we're saying there are certain sets of vectors that if we multiply a matrix A by x, we get back the same exact vector x times some scalar. And there's only going to be a certain class of vectors that this is true for. In general, it's not true. But if it is true, we call the vector an eigenvector, and we call this lambda, this scalar, an eigenvalue, and they're paired. So this is the eigenvalue associated with this eigenvector, or vice versa. And so when we think about this, just in describing this problem statement, this vector is some n by 1 thing, and this matrix is some n by n thing. And how do we know that that's true? This is an n by 1 thing. If I times it by a scalar, which is 1 by 1, I know I'm getting an n by 1 thing, so this must be an n by n thing, so that when I multiply these together, I get an n by 1 thing. And so just even stating this eigenvalue eigenvector problem, you're implicitly saying that A is a square matrix. This problem doesn't even make any sense if A is rectangular. So this only applies to square matrices. So it's trivial that the zero vector always satisfies this. If I take A times a zero vector, I'll always get out 0. And so you could always write it like this and say, well, and this, what's the scalar? 1, 10, a million, who cares? So it doesn't really make any sense to talk about this for a zero vector, because of course if I multiply a matrix by a zero vector, I get back out the zero vector. So we don't count the zero vector, just like in a lot of things with linear algebra. But any x not equal to 0 that satisfies this equation is an eigenvector of this matrix A. And that's the way you state it, that x is an eigenvector of A, and lambda is an eigenvalue of A, and they come in a pair like that. So let's try and solve this equation. So if we believe this exists, we believe there's some special vector that this is true for, let's try and solve for that vector. So we have this equation. Let's just bring the right side over to the left. So we minus like this, and we say this is equal to now a 0 vector. So this is an n by 1 thing, an n by 1 thing, and this is an n by 1 0 vector. Now we could be tempted to try and factor the x out to solve for x and do something like this, where we write a minus lambda x equals 0, but we can't do that because this doesn't make sense, because this is an n by n thing and this is a 1 by 1 thing, and you can't add and subtract things that are the wrong dimensions. So we again, as before, we recognize this trick that this thing here is really just the exact same thing as saying ax minus lambda times n by n identity matrix times x, because if I multiply any vector by the identity matrix, I get that vector right back. And so by doing that, it does allow us to factor that whole term out. And so now we're taking an n by n thing, subtracting an n by n thing. And so this is equal to the 0 vector. So for any x lambda pair that this is true for, then this is also true. So what does that mean? We've already decided we're considering only cases where x is not equal to 0, right? Because 0 is a trivial case. So we know x is not equal to 0. So what does this equation fundamentally tell us? It tells us x is in the null space of this matrix A minus lambda I, which is some n by n matrix. So x is in the null space. So if we're going to talk about the null space, then maybe we should think about the dimension of the null space. And from the linear algebra review, we know how to find the dimension of the null space. What we do is we look at the rank of A minus lambda I. And if we find the rank of A minus lambda I, that is equal to the number of linearly independent columns of A minus lambda I, which is also equal to the number of linearly independent rows of A minus lambda I. And if we find the rank, we know that the rank of this plus the nullity, which remember is the dimension of the null space, have to equal the number of columns. So they have to equal n. So if we look at this matrix A minus lambda I, subtract that from the number of columns, we'll get the nullity, and we can see the dimension of the null space. And so what that effectively tells us is it tells us how many vectors, how many linearly independent vectors x make this equation true for the same lambda, meaning that potentially if the nullity is 1, it means there's exactly one x that this is true for a given lambda. If the nullity was 2, then there'd actually be two different vectors x that are linearly independent from each other because they're forming this null space that both make this equation true for the same lambda. So this is actually possible. So the very fact that x exists and is in the null space of this equation, because we're saying x is not a zero vector, yet I take some non-zero vector, times it by this matrix, and I get the zero vector, that means that a null space exists. Just the fact that x exists in our hypothesized eigenvector eigenvalue equation means that we're saying that this matrix has a null space. And having a null space means this matrix is not full rank. So the one thing we know is that the rank of this matrix A minus lambda I is definitely less than n. It's not full rank. We don't know what it is, but it's not full rank because this wouldn't exist if it were full rank. So we also know that it's singular if it's not full rank. So if it's singular, what does that mean? Singular means the determinant singular. This means that the determinant of this matrix, A minus lambda I, is equal to 0. And we call the determinant of A minus lambda I, sometimes we call this some function, which I'll call delta lambda, which we call the characteristic equation. And I'm not going to review how to solve for determinants. You can do that yourself. And solving for 2x2 and 3x3 matrix determinants is very easy, and you should be able to do it by hand. But when you do that, you're going to get, if A is an n by n matrix, then this thing is going to be an nth order polynomial in lambda. So it's an nth order polynomial for an n by n matrix. And so we call this the characteristic equation, we call this the determinant, and in the cases where you really are truly at an eigenvalue, then this characteristic equation is going to equal 0. It's not always 0, it's only 0 at an eigenvalue. In cases where if you plug in a non-eigenvalue value, you'll still get a characteristic equation, it just won't be set equal to 0. So the thing I want to make sure is coming clear is there are going to be, you can plug in any number into this characteristic equation, and we'll work out some examples in a second, but only those numbers that equal 0 occur when they're paired with some x that is the associated eigenvector that they belong with. So I want to work out a couple of examples really quickly to kind of see how, in some simple examples that you can wrap your head around, that will help us kind of hopefully ground some of these things home. So let's first begin with what we call a simple eigenvalue problem. And what simple eigenvalues means is that no eigenvalues are repeated. So we have a matrix that's an n by n matrix, and it's going to have n eigenvalues, but we want to say all those eigenvalues are different. So let's start with a matrix, a really simple matrix, so we can do it by inspection to begin with. So let's say 2, 0, 0, 5. And it's pretty easy for me just by inspection on a diagonal matrix like this to find the eigenvalues. And it's really easy because they're just like the simple unit basis. So if I take this matrix and I multiply it by this vector, I get 2, 0. But then if I factor that 2 out, that's just 2 times 1, 0. So immediately I see, okay, this actually is an eigenvector, v1, because I'm getting the same vector out, and this is its associated eigenvalue, lambda 1. The same thing goes if I take this matrix and I multiply it by this vector, I'll get out 5, and then I can factor the 5 out, and I'm getting back the same vector I put in. So this vector is our second eigenvector, and this is its associated eigenvalue. So 2 and 5 are eigenvalues of this matrix A, and these are the associated eigenvectors. Now, I happen to call 1, 0 eigenvector 1, but they're really scale independent. It wouldn't have mattered. Like if I would have taken, let's say I would have instead taken this matrix and I would have multiplied it by 10, 0. What would I get out? I would get out 20, 0, and I could factor a 2 out to get back the original 10, 0. So in this case, I would have said this was an eigenvector because I'm putting the same vector in that I'm getting out, and this is the associated eigenvalue. So what did we learn from this? Let's compare these two conditions. The eigenvalue didn't change. 2 was the eigenvalue, and there's no question about that. But the associated eigenvector with that eigenvalue, it could have been 1, 0, it could have been 10, 0, it could have been minus 5, 0. All that really matters is it's this vector or any scalar multiple of this vector. They're all valid eigenvector 1s. And the same thing would have gone for eigenvector 2. It's got to point in the right direction, but it doesn't have to be the exact length. So eigenvectors do not have to be unit length. We often do that just for simplicity. So now we solved for these eigenvalues and eigenvectors from inspection, but this isn't a rigorous routine that you could do over and over. So I want to make sure we can do the rigorous routine and show that we get the exact same values. So what we're really trying to solve in general is we're trying to solve this equation, that the determinant of A minus lambda I is equal to 0 if lambda is an eigenvalue. So let's look at this matrix, A minus lambda I. So our original matrix was 2, 0, 5, 0, and we're going to subtract lambda times the identity matrix, so that looks like this. And when we're done, we get a matrix that looks like 2 minus lambda, 5 minus lambda, 0, 0. And so we don't need to repeat this process over and over because it's always the same. This matrix, it looks exactly like the original A matrix, and then you put a minus lambda on all the diagonal elements, and you don't touch the off-diagonal elements. Okay, so now we're going to take the determinant of A minus lambda I, and for 2 by 2 matrices, that's really simple. It's this term times this term minus this term times this term. So 2 minus lambda times 5 minus lambda minus 0 times 0, and the determinant's going to equal 0, so this equals 0. So I can do this math, and I can say this is 10 minus 2 lambda minus 5 lambda, so that's minus 7 lambda, and then plus lambda squared equals 0. And I'm going to write this in a format that we're usually used to seeing these kind of polynomials. Okay, now how do I solve for lambda? Well, we have a simple formula for this, and we usually structure it in this way, and then we say it's negative b plus or minus the square root of b squared minus 4ac, so 4 times 1 times 10 is 40, all over 2a, so that's 2 times 1. And then I look at that, and it's 49 minus 40 is 9. Square root of 9 is 3. So that's 7 plus or minus 3 over 2. And then I realize there's two solutions to that. Lambda 1, let's call that 7 plus 3 is 10 over 2 is 5. And lambda 2, 7 minus 3 is 4, divided by 2 is 2. So we get the same eigenvalues that we got by inspection before, but this routine is more rigorous, and you could repeat it. So one eigenvalue is 2, and one eigenvalue is 5. So how do we find the eigenvectors in general associated with these matrices? So I say, if this truly is an eigenvalue, then this matrix A minus lambda I with lambda 1, let's say, has an associated eigenvector 1, and when I do that, I'm going to get the 0 matrix. So let's write A minus lambda I. So that looks like 2, and so what is lambda 1? We said in this case lambda 1 was 5. So let's keep with that. So 2 minus 5, and then 5 minus 5, 0, 0. And then let's break this vector 1 up into little scalar components. So we have a little component 1 and a little component 2. And I won't put the bar to show these aren't vectors. These are the scalars that go inside of here. And that's going to equal the 0 vector. So I work these equations out, and this top equation becomes minus 3 times v1 is equal to 0, and the bottom equation becomes 0 times 0 equals 0. So this is just worthless. And so when I boil this down, I only get one constraint. Minus 3 v1 equals 0 means that v1 has got to equal 0. But there's no constraint on the second element at all. So when I say lambda 1 equals 5, what is the associated eigenvector associated with that? Well, the first entry has to be 0, and the second entry can be whatever we want. And so since it can be whatever we want, let's just put a 1. So we got the exact same eigenvalue eigenvector pair that we got by inspection, but this is a routine that you can repeat over and over, and you won't have any problems. So we also can think about the rank of this matrix that we were talking about before and say, is this the only vector of this? So what is this matrix that we worked out here? This matrix ended up being minus 3, 0, 0, 0. So if this is A minus lambda I, then its rank is equal to 1. There's one linearly independent column. But if there's one linearly independent column and rank of 1, and we have two columns, you put those two facts together, and it says our nullity is equal to 1. So we have a one-dimensional null space for this matrix. So not only did we find a eigenvector that's associated with this matrix, but we found the only eigenvector that's associated with it. So the next thing I want to look at is something where we don't have simple eigenvalues. So we're going to consider an eigenvalue with multiplicity 2. So if we do that, let's consider this matrix here. If we do this, it's very easy. If we go through the calculations using the determinant, it's very easy to see that lambda 1 equals 2 and lambda 2 equals 2. So we have two eigenvalues here, and we can say we have one eigenvalue with multiplicity 2. That's the way to describe it, and that one eigenvalue is 2. So the question is, are there two eigenvectors associated with this eigenvalue? And the way we can do that is we can again look at this matrix, lambda I, and look at its rank. So let's do that. Let's find A, which is this matrix 2, 2, 0, 0, minus lambda I, lambda, 0, 0. And that looks like 2 minus lambda here, 2 minus lambda here, 0, 0. And we already know what our lambda is. It's 2. So if we plug that in, what do we get? We get 0, 0, 0, 0. So what's its rank? Its rank is 0. We have no linearly independent columns. And since there are two columns, this implies that our nullity is 2, because the nullity plus the rank has to equal the number of columns. So our eigenvector space is a two-dimensional space. And so any vector that satisfies this 0, 0, 0, 0 times any vector here, v1, v2, equals 0, is an eigenvector. But every vector satisfies this. So for a matrix like this, a diagonal matrix with repeated eigenvalues, any vector is an eigenvector. So that's a very interesting result, but it kind of makes sense if you think about it. I mean, we're talking about a matrix 2, 0, 0, 2. That's nothing more than 2 times the identity matrix. And so if I take this matrix 2, 0, 0, 2, and I multiply it by some vector v, that's the same thing as just going 2 times the identity matrix of v, which is the same as 2 times v. So for a really simple case like this, once you step back and look at it, you go, yeah, any vector is an eigenvector, and the eigenvalue is 2 because it's really just 2 times the identity matrix. Now let's consider one where we've just made one slight change. So let's consider this matrix that looks like 2, 2, and then let's just stick something up here. Let's say a 1. So this is my A matrix now, and I want to know what are its eigenvalues and eigenvectors. Okay, so we're going to look at the determinant of A minus lambda I and set that equal to 0. And when we do that, we get the determinant of this matrix 2 minus lambda, 2 minus lambda, and then the diagonals are untouched, and then that's equal to 0, and so we get 2 minus lambda times 2 minus lambda minus 0 times 1 equals 0, but this just isn't doing anything because it's being multiplied by 0, and so again we're getting the exact same eigenvalues, 2 and 2. Same eigenvalues as before. So the eigenvalue again is 2 with multiplicity 2. But the matrix isn't the same. The matrix before was this diagonal matrix that was 2 times the identity matrix. That's not what our matrix is now. So we have the same 2 eigenvalues. The question is, do we have the same 2 eigenvectors? So if I take this matrix now, A minus lambda I, where lambda is equal to 2, what do I get? I get this matrix. So 2 minus 2 is 0, 0, 1, and 2 minus 2 is 0. Last time we did this, we got the 0 matrix. But now we have this 1 sitting here. So this matrix is not rank 0. This matrix is rank 1. And if there's 2 columns and it's rank 1, then our nullity is equal to 1. So now we still have an eigenvalue of 2 with multiplicity 2, but our dimension of our null space of this matrix is only 1. So there's only going to be one eigenvector associated with this eigenvalue, even though the eigenvalue appears twice. And so we can solve for what that is. We can say, okay, if I have this matrix 0, 1, 0, 0, and I multiply it by some vector, v1, v2, like this, it's got to equal the 0 vector. So what are the equations I get? The top equation is 0 times v1 plus 1 times v2 equals 0, so v2 equals 0. The bottom equation is 0 equals 0, and that doesn't tell us anything. So we only have one real constraint, and that's v2 equals 0. So what is the eigenvector associated with this eigenvalue? It is 0 and anything. And if I can have anything, I'll just put a 1. So this is the eigenvector for this eigenvalue. And the eigenvalue appears twice, the eigenvector only appears once. And it's the only eigenvector there is. So we have to be careful when we're looking at eigenvalues when the eigenvalues are all distinct, and so that means they're simple, meaning not repeated. Then for each eigenvalue, there will be a distinct eigenvector. When the eigenvalues are repeated, there may be a distinct eigenvalue for each eigenvector, or each eigenvalue, even though it's repeated, or there may be less eigenvectors than there are eigenvalues. And we'll return to this in the future.